Something just happened in quantum computing that most people have no idea about, and it could completely change who wins the race to build the most powerful computer humanity has ever created. IBM didn't just make an announcement. IBM crossed a line that scientists have argued about for years, a line called quantum advantage. And they did it not once, but 3 separate times on the very same day. Meanwhile, over at Microsoft, a company that just months ago proudly moved up its own quantum timeline, engineers are suddenly facing a very uncomfortable question. Is their 2029 promise still realistic, now that IBM is already delivering real results? Let's slow down and actually explain what quantum advantage means, because this term gets thrown around constantly without proper context. Quantum advantage is the specific moment when a quantum computer solves a real problem better than every single classical computer on Earth, including the most powerful supercomputers ever built. It is different from something called quantum supremacy, which just means a quantum machine did something unique, even if that something wasn't particularly useful. Advantage means usefulness. Supremacy just means novelty. This distinction matters enormously because the industry has been burned before. Google claimed quantum supremacy back in 2019 with its Sycamore processor, but critics quickly pointed out that the specific problem it solved had almost no real-world value. It was fast, but it wasn't useful. That single event created years of skepticism, with the phrase quantum supremacy becoming almost synonymous with marketing hype rather than genuine scientific progress. IBM seems to have learned from that history, and their approach this time is completely different. On July 30th, 2026, IBM revealed 3 separate demonstrations of quantum advantage on the exact same day, and every single one of them was submitted to something called the Quantum Advantage Tracker. This is not just an internal IBM tool. It is a public system that invites the entire global research community to challenge and attempt to disprove IBM's results using classical computing methods. In other words, IBM isn't just claiming a win. They are publicly daring the world to prove them wrong, and so far, nobody has succeeded. Let's break down what those 3 demonstrations actually involved, because each one attacks the problem from a different angle. The first involved IBM working directly with the University of Chicago to demonstrate quantum advantage using something called logical circuits. These are encoded quantum circuits that have been specifically verified to perform calculations beyond what any leading classical simulation method can currently achieve. This represents one of the largest demonstrations of logical quantum computing ever recorded. And logical qubits matter because they are the building blocks of error-corrected, reliable quantum systems, not just experimental prototypes. The second demonstration came through a partnership with Algorithmic, a quantum software company founded in Finland and currently operating out of Milan. Together, they simulated something called heterogeneous quantum matter, a genuinely complex physics problem. What makes this particular result so striking is that it had already been sitting on IBM's public quantum advantage tracker for 8 full months, openly challenging researchers everywhere to beat it using classical methods. During that entire 8-month window, not a single classical approach successfully matched IBM's results across the complete range of the problem. That's not a quick, flashy stunt. That's sustained, tested, real advantage. The third demonstration might be the most technically important one, and it came through a partnership with an Israeli company called Kedma Quantum Computing. Together, IBM and Kedma showed what they are calling trusted quantum advantage, using a system of 70 logical qubits combined with an entirely new error correction method. Their experiment successfully completed a computation that no leading classical simulation method could match, while simultaneously providing statistical proof that the quantum result itself was actually accurate. That second part is critical because quantum computers are notoriously difficult to verify. Unlike a normal computer, where you can just rerun a calculation somewhere else to check the answer, some quantum results push so far beyond classical capability that there's no easy way to confirm they're correct. Proving both speed and trustworthiness at the same time is a genuinely rare achievement. Analysts at research firm IDC were quick to weigh in on what this actually means for the industry. Heather West, an analyst focused specifically on quantum computing, described these results as another meaningful milestone on the road toward using quantum systems to solve problems that sit far beyond the limits of classical computing. She was also careful to add some healthy perspective, pointing out that reaching quantum advantage isn't going to be one single dramatic moment, unlike the sudden cultural explosion that ChatGPT triggered across the entire AI industry. Instead, she expects a steady stream of announcements, each one building on the last, gradually pushing the technology further forward. This wasn't some sudden surprise move either. IBM has been publicly building toward this exact moment for months. Back in November 2025, the company laid out a clear roadmap during its Quantum Developer Conference, stating plainly that it expected verified quantum advantage to arrive sometime in 2026, with a much bigger target of full scale, fault-tolerant quantum computing arriving by 2029. At that same event, IBM unveiled a new processor called Nighthawk, built with 120 qubits and 218 tunable couplers, connecting each qubit to its 4 nearest neighbors. Jay Gambetta, who leads IBM research, said at the time that IBM believed it was the only company positioned to rapidly invent and scale quantum software, hardware, fabrication, and error correction all together, unlocking genuinely transformative applications. Then, just a few months later, IBM's own CEO Arvind Krishna doubled down on that same message during the company's first quarter 2026 earnings call. Krishna pointed directly to a series of recent technical milestones and strategic partnerships as clear evidence that IBM's long-term quantum strategy was finally starting to produce measurable real-world results. He reaffirmed that IBM remained firmly on track to deliver a large-scale, fault-tolerant quantum computer by 2029, a system specifically designed to correct its own errors and reliably run extremely complex calculations. Now here's where the story becomes genuinely fascinating, because IBM is far from the only company chasing this exact same 2029 target. Microsoft has been running its own aggressive quantum program, built around a completely different physical approach called topological qubits. In June 2026, Microsoft unveiled a new processor called Majorana 2, and the announcement was honestly stunning on its own. Microsoft claimed a 1,000 times improvement in qubit reliability compared to its earlier Majorana 1 chip, achieved by swapping out the original aluminum-based superconducting material for lead instead. That single material's change pushed qubit lifetimes from roughly 2 milliseconds all the way up to 20 seconds on average, with some individual measurements lasting over a full minute. Based on those results, Microsoft made a bold decision. The company slashed its own original quantum timeline in half, moving its projected delivery of a scalable, commercially valuable quantum computer from a distant 2035 target all the way up to 2029. That's the exact same year IBM has been targeting for fault-tolerant quantum computing. Suddenly, two of the biggest names in global technology are racing toward the identical finish line using two completely different underlying technologies. Microsoft's approach is built around what they call a hardware-protected topological core, essentially betting that a fundamentally different physical structure can avoid the massive overhead of physical qubits that traditional quantum error correction usually requires. If Microsoft's bet pays off, it could offer a highly scalable path toward a system containing 1 million qubits on a single chip. That's an enormous claim, and it explains why Microsoft has been so aggressive about defending its approach despite serious scientific pushback. And there has been serious pushback. Microsoft's original Majorana 1 announcement back in February 2025 was met with real controversy within the scientific community. Researchers raised pointed questions about whether the topological states Microsoft claimed to observe were genuinely as clean and reliable as the company suggested. That skepticism didn't disappear overnight, and it means Microsoft's newer Majorana 2 results are being scrutinized even more closely than a typical announcement would be, precisely because of that earlier controversy. So here is the real tension driving this entire story. Microsoft is betting everything on a single, unproven, but potentially revolutionary architecture, racing to prove that topological qubits can leapfrog the entire industry through sheer physical elegance. IBM, meanwhile, is playing a very different game. They are betting on incremental, continuously validated progress, using superconducting qubits refined over many years, while simultaneously hedging with a second physical approach entirely, spin qubits gained through their recent acquisition of HRL laboratories from Boeing and General Motors. That HRL acquisition suddenly looks even more strategically important in this context. While Microsoft is putting enormous weight on one single bet with topological qubits, IBM is deliberately spreading its risk across multiple physical approaches at once. If superconducting circuits eventually hit a wall, IBM already has spin qubit expertise waiting in the wings. Microsoft doesn't have that same kind of built-in insurance policy. This is exactly why IBM's July 30th announcement lands with so much weight right now. It's not just that IBM achieved quantum advantage, it's the timing. IBM delivered 3 separate, independently verifiable results, openly inviting global scrutiny. At the exact moment, competitors like Microsoft are staking massive public claims on a much narrower, more contested technological bet. Every time IBM adds another verified result to its public tracker, it raises the bar that Microsoft's own Majorana approach will eventually need to clear, using completely real-world, checkable evidence rather than theoretical promises. It's worth being clear that plenty of skepticism still remains across the wider quantum industry. Analysts at firms like Next Platform have pointed out that several companies have made quantum advantage claims over the past few years, only to face intense scientific debate afterward. Google's own Willow chip generated headlines with something called the Echoes algorithm, A company called QCTRL claimed evidence of practical quantum advantage in materials science while running its software directly on IBM's own quantum platform. Even D-Wave made competing claims involving quantum annealing systems, and those claims were challenged too. The difference this time is that IBM specifically built its announcement around continuous, public third-party verification, rather than a single dramatic headline moment. There's also a deeper industry context worth understanding. Investment into quantum computing has been surging dramatically, more than doubling during just the first quarter of 2026 alone. There are now roughly 80 major quantum computing companies operating around the world, alongside hundreds of smaller startups crowding into the same space. That kind of explosive growth typically signals real momentum, but it also creates enormous pressure for every major player to announce something, anything, that keeps investor confidence alive.